So in chapter 7, we're going to start working with sequences and series. In section 1, we're just going to give sort of an overview of what the sequences are and talk about some special types of sequences. And as we move through, we'll learn more details about sequences. So a sequence is basically, again, just it's a set of ordered pairs, right? It's still an input and output, but we have a little more direction on our independent variable x. It's always a sequential set of numbers. It's 1, 2, 3, 4, 5, 6. This is why it's called a sequence, is because rather than having a wide variety of an infinite number of different inputs, we're going to use very specific inputs, numbers in sequence. That's why it's called a sequence. And when you talk about terms of a sequence, those are the outputs. Okay, and a term's place in the sequence is related to its input. So this would be the first term, the second term, the third term, the fourth term, the fifth term, and the sixth term. So we're really talking about functions in a way that we have in the past, and yet we're adding this new wrinkle that we're very specific about what the inputs are. They're sequential. And now we're starting to name the terms based on what the input was. So this would be a sequence if when I had these outputs all filled in. The terms of the sequence would be the outputs. When you talk about a series, that's taking a section of the terms, so a range of the terms, and finding their sum, adding them together. Summation notation is an abbreviation for how to write an instruction to put together a series. It involves sigma. So summation notation and sigma notation, they're the same. And what you always have is you have the rule of the sequence over here on the right. Sigma tells you find the sum of. Underneath you'll have something like n equals 1 or n equals 0. That's which term in the sequence will you start with. And up here you'll find out how many terms are you going to find. So this would be find the sum of the first 4 terms. That's what this says from this particular sequence. And we'll go through how do you go ahead and find those sums. Right, so a type of problem I might try to address with this is a regular pattern here where we're stacking apples in the shape of a square. It's got 7 layers, so now we're looking at writing a rule for how big each layer is. And what's important to think about with the pyramid is that the base of the pyramid is always a square. So when we go through and we work with this, we're going to go ahead and create the sequence and then put it in a graph. Okay, so some of the information I've already gone through with you. A sequence is a function whose domain is a set of consecutive integers or sequential integers. Okay, so if they don't tell you what the domain is, it's understood, right? So you automatically should assume that if they don't give you any further information, that the domain begins with 1. So you'll always start with the first term. The values in the range are called the terms of the sequence. So the outputs, which would be the range, those are the terms. And the inputs or the domain, those are always sequential numbers. A finite sequence has a specific stopping place. You'll see 2, 4, 6, 8. This is 4 terms. It's finite how many terms there are. An infinite sequence continues on forever. So you see this dot, dot, dot. That's the important thing for you to notice. If you see the dot, dot, dot at the end, that means it's an infinite sequence and it doesn't have a stopping point. Okay, and sequences can be specified by a rule. We're going to work a lot with how do you write the rules of sequences. You could think of the rule as an equation, okay, for the function. So if I want to write the terms of a sequence, let's say I want to write the first 5 terms. What's important then is when you say a sub n is an unknown place in the sequence. So when n is equal to 1, a sub 1 would be equal to 1 plus 2. When I find the second term in the sequence, a sub 2, that means the second term in the sequence would be 2 plus 2. So this will equal 3. This will equal 4. A sub 3 would be equal to 3 plus 2, which is 5. A sub 4 equals 4 plus 2, which is 6. And A sub 5 would be equal to 5 plus 2, which is 7. So what's important for you to remember is you'll notice that which term it is, the ends are the same. So when I find the first term, I plug 1 into the function. When I have the second term, I plug 2 in, and so on. Okay, so these values of n match. So you can have a sequence like this, which is really simple and familiar. This is a little different. A sub 1 would be equal to 4 to the 1 minus 1 power, which would be 4 to the 0 power, which is 1. A sub 2 would be 4 to the 2 minus 1 power. 4 to the first power is 4. A sub 3 would be 4 to the 3 minus 1 power. 4 squared is 16. A sub 4 would be equal to 4 to the 4 minus 1 power. 4 to the third power is 64. And then a to the fifth power would be equal to 4 to the 5 minus 1 power. 4 to the fourth power is 256. Okay, so again, what you're doing is you're picking which term and putting that term location, the term's place from the sequence, into your function in place of n. Just like if I was saying when x was equal to 1, I'd plug 1 in for x. It's exactly the same. Okay, so go ahead and practice a little bit of this. Do problems 5, 6, 8, and 9. They're very easy. And then come on back and we'll talk about this a little more. Okay, so now if I want to write the rule for a sequence, this becomes, what you want to look at is what happens and what changes. So in section 1, we're going to talk a lot about just sort of like figuring it out. Right? And so what you want to do is you want to look at what changes as I go from term to term. Come up with an idea of what you might do to make it work. And then go ahead and write the rule and test for validity. So when I look at the numerator and the denominator, they're doing different things here. So I can see that my numerator is changing by 2's. Okay, so I could say that that normally means that it's 2 times the sequence. And down here it's changing by 10, so that would be 10 times the sequence. And now if I test this, a sub 1 would be equal to 2 over 10. Oh, but I need 1 over 10. So I'm off by 1. Let's try the second term. A sub 2 would be equal to 2 times 2, which would be 4 over 20. So my denominator is fine, but you see that my numerator in both cases 1 off. Well, if I just put in a minus 1, now I can go ahead and a sub 1 would be equal to 2n, 2 times 1 minus 1, that's 1, over 10 times 1 is 10. A sub 2 would be equal to 2 times 2, which is 4, minus 1, which is 3, over 10 times 2, which is 20. And now you see that I'm getting the right values. 3 times 2 is 6, minus 1 is 5, and 3 times 10 is 30. So this is the rule that makes this sequence. So what I did is because it was a fraction, it's more difficult. I have 2 different relations going on. I wrote an estimation of what would work for the numerator and an estimation of what would work for the denominator. I tested it. I found I had a problem. I readjusted for the problem. I tested again, and now I find that my solution is valid. That's sort of the way to go about these things. Okay, so now let's take a look at this guy. I can see that if I'm changing by 4 every time, I could say 4n, that would work. That'll make a change of 4 every time. So then a sub 1 would be 4, that's not right. A sub 2 would be 8, that is right. A sub 3 would be 12, that's not right. And a sub 4 would be 16, that is right. So this one's right, and this one's right, and this one's wrong, and this one's wrong. So I'm having problems with all these odd guys because they're supposed to be negative numbers. So maybe what I need to look at is I need to find a way then to alternate from negative to positive, negative to positive. Well, if I take a negative number, let's say -1, to the n power, then whenever n is odd, like this or this, it will be negative. But whenever it's even, like this, it will be positive. And that's what I want. So these don't work. Half of them worked, half of them didn't. Now if I use my new rule, a sub 1 would be equal to 4 times 1 times -1 to the first power. So 4 times 1 is 4 times -1 is -4. A sub 2 would be equal to 4 times 2 is 8 times -1 squared. -1 squared is +1. 8 times +1 is 8. Okay, so now that one's right and that one's right. Let's try one more. A sub 3 would be 4 times 3, which is 12, times -1 to the third power, which is -1. That's -12. Okay, so now I'm getting the right things. So again, hypothesize what will work, test it, then adjust. Okay, if you have alternating negatives like this, taking a negative number to the n power will help make that sort of thing happen. So these are typical patterns you can see. You'll notice as I change 2 each time, the 2 becomes a coefficient. As I change by 4 each time, the 4 becomes a coefficient. These are things to help guide you as you go ahead and try this out. So try problems 15 and 19, and then come back and we'll talk about more. So now when we talk about series, remember a sequence is a collection of inputs and outputs. A series is finding the sum of a range of outputs. So you can look at finding the sum of a finite series, so a specific number of terms, in this case 4 terms, from the first term to the fourth term, from this function. I could do that. Here it wants me to go from 1 to infinity in this. This is not possible to find the sum of, because if we're going to infinity, each new term, you can see these terms are getting bigger each time, bigger by 2 each time. So here I would not be able to find this actual sum. Okay, so even though I can write it, I can't actually calculate what its value is. This one, fine, 4 terms. Here are the 4 terms. 2 plus 4 is 6, plus 12, or plus 6 is 12, plus 8 is 20. This one would equal 20. This one is undefined. I can't actually calculate it. What's important though in summation notation, as I mentioned at the very beginning, is you use sigma. That means find the sum of. It's an instruction. This tells me where to start, this tells me where to end, and this tells me what the rule is, so I can actually make the terms if necessary. Right? When we look at doing this, write the series using summation notation. Okay, so for here, I see it's an infinite series. I'm always told to assume, right, there's no dot, dot, dot on this side. This must be the first term. So I'm starting with the first term, and I'm going to infinity. Now I want to write the rule. Well, I see I'm changing by 2 each time. So I could do 2 times n, but you notice that this would give me 2, 4, 6, 8. So I'm off by 3 in each case. So I'm going to add a -3. If I want to double check this, a sub 1 would be 2 times 1 minus 3, that's -1. A sub 2 would be 2 times 2 is 4, minus 3 is 1. So I'm getting this correctly. A sub 3 is 6 minus 3 is 3. Okay, so that's how I wrote the rule, and this is summation notation. We're going from the first term to the infinity term, and this is what it looks like. Okay, now this is a finite series. There are 1, 2, 3, 4, 5, 6, 7 terms. So I know I'm starting with the first term and I'm looking at 7 terms. Now I need to write the rule. Well, 1, 2, 3, 4, 5, 6, 7, that's very simple. That's just n. Right? And these 4, 5, 6, 7, 8. So it changes by 3, n plus 3. Okay, if I want to test this, a sub 1 would be 1 over 1 plus 3, which is 4. Correct. A sub 2 would be 2 over 2 plus 3, which is 5. Correct. I'll try one more, but I know this is correct. So I'll have 3 over 3 plus 3, which is 6. Okay, so these all check out. My rule is correct. And this is how you write summation notation. So again, get a little practice on this. Do problems 41 and 42. And then come back. So if I actually want to find the sum of the series, what I need to do is I'm going to need to write these terms. So the first term through the sixth term. And then I'm going to want to add them up. So a sub 1 would be 2 times 1, which is 2. A sub 2 would be 2 times 2, which is 4. A sub 3 would be 6. A sub 4 would be 8. A sub 5 would be 10. And A sub 6 would be 12. So if you take a look at this, let's see, 8 plus 12 is 20, plus 10 is 30. These add up to be 30, and these add up to be 12. So this is 42. Okay, so that's finding the sum of the series in this section. Later, as we move forward, we're going to find some shortcuts to make this a little easier. When we look over here, I want to only need to find 4 terms. So 3 times 1 squared is 3. 3 times 2 squared, well, 2 squared is 4 times 3 is 12. A sub 3, 3 squared is 9 times 3 is 27. And 4 squared is 16 times 3 is 48. Okay, so 48 and 12 is 60, 87, and 3 is 90. Okay, so I found the number of terms, I added them together, and that was that. All right, now we have some special cases, right, which don't get used, quite honestly, don't get used a whole lot, but we're going to use one of these guys in some of the other work we're going to do. Well, in terms of solving that word problem, we might be using this guy. But if we look at finding the sum of 35 terms, you see from 1 to n terms of a sequence called 1, it would just equal the number of terms. 35 ones added together makes 35. Right now, if I have n, this is going to be, right, 1 plus 2 plus 3 plus 4 plus 5, all the way up to 16. I can shortcut this by just taking the number of terms we're doing and plugging that in. Okay, 2 goes into 16 8 times. 8 times 17 would be 80 and 56, that's 136. Okay, and when you take a look at this guy, same deal, I'm going to do 18 times 18 plus 1 times 36 plus 1, all divided by 6. 6 goes into 18 3 times, so this is going to be 3 times 19 times 37. I'll probably go ahead and put out a calculator for that. So 3 times 19 times 37 equals 2109. Okay, so these are special cases, special series. Once you identify what it is, take the value of n, plug it in, and you can go ahead and simplify. Now when we take a look at this guy, we want to write a rule for the number of apples in each layer. Well, you can see the first layer here at the top. Now they're being very specific that the top is the first layer, not the bottom. The first layer is the top, so this is 1. And the bottom, the next layer is 2 by 2. And the next one is 3 by 3. So you can see that each layer is the square of the layer. So I know that a sub n is equal to n squared, because when I have a sub 1, that'll be 1. A sub 2 will be 2 times 2, which is 4. A sub 3 will be 3 times 3, which is 9. A sub 4 will be 16. And I'm going ahead and writing it out because it's asked me to graph the sequence. So I've come up with my idea. I'm testing it. It is correct. I'm making an input-output table. And then I'm going to graph it. Okay, so it's pretty straightforward. I Actually, let's use this one because they're all positive numbers, so I don't really want to. So if I go ahead and create my input-output table and try to graph this, I'm going to go right 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is 20, 10 up, 10 across. So if I go by twos or so, this shouldn't be too bad. Right? So here's my first point, 1, 1. Then my second point is 2, 2, 4. And then 3, 2, 4, 6, 8, 9. And then, sorry, 1, 2, sorry, 9 was supposed to be right here. And then 4 is 2, 4, 6, 8, 10, 12, 14, 16. 5 would be 25. Right, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 25. So you see my graph does this. This is an exponential function, right? So this is the process, and what you need to get used to is the idea that you're going to come up with an idea of what you think the rule is. You want to test it for validity. In this case, my idea, I looked at it, it's pretty straightforward, it made sense. I tested it, it's accurate, and then I can go ahead and graph it. If it's not accurate, I want to do an adjustment and keep testing until I get it to be accurate. So that's how you work with sequences and series.